A new logistics chain is forming to deliver cargo to the Moon, creating the basis for sustained lunar exploration. This effort is led by NASA's Commercial Lunar Payload Services, or CLPS program, a public and private. The goal is to send numerous small robotic landers and rovers to different regions of the Moon. Zooming out reveals the Earth and Moon system, showing the scale of the long-distance journey. The lunar surface itself holds key resources and unexplored regions which CLPS aims to study. The South Pole is a primary target due to water ice in permanently shadowed craters. Now we examine why NASA chose this commercial approach for lunar delivery. Traditional government-led missions are often very expensive and have long development cycles. By contrast, the CLPS model uses fixed-price contracts with private companies for specific delivery tasks. This strategy transfers some of the financial risk and encourages rapid innovation from the private sector. Companies compete for task orders to build landers and provide a complete transportation service. This competitive environment helps to lower the total cost of delivery for the science payloads. Let us look at how a CLPS mission is structured, starting with the payloads. NASA provides the scientific instruments and technology demonstrations, the cargo for the landers. These payloads can be small cameras, radiation sensors, or miniature rovers. Each payload must survive the harsh launch and landing environment on the Moon. The CLPS providers design and operate the lander vehicle, integrating the NASA cargo. The provider is responsible for selecting the launch vehicle and the trajectory to the Moon. The task order specifies the target landing site, the total payload mass, and mission duration. The fixed price is paid only when the lander successfully delivers the payload to the Moon. The logistics chain begins with the launch, often using commercial rockets like Falcon 9. The lander vehicle is housed within a payload fairing, protecting it during the ascent through the atmosphere. After fairing separation, the rocket performs the trans-lunar injection burn, sending the lander toward the Moon. The trajectory is typically a long, energy-efficient path lasting several days or weeks. On the diagram, we see the lander's initial trajectory, a multi-day transfer orbit. The lander uses its own small thrusters for mid-course corrections during the cruise phase. These course corrections ensure the lander is perfectly aimed for a lunar orbit insertion burn. The communication path must be maintained throughout the entire mission, often via the deep space network. The lander engine fires to slow down and achieve a stable circular orbit around the Moon. This lunar orbit insertion is a critical, high-risk maneuver requiring precision burns. Once in orbit, the lander prepares for the terminal descent and the complex landing sequence. We will now focus on the engineering required for a soft, controlled lunar landing. On the diagram, we see a typical CLPS lander, such as the Nova-C or Peregrine vehicle. The lander is primarily composed of the propulsion system, structure, and payload deck. The main engine must provide a deep throttling capability to control descent velocity. The engine fires against the lander's direction of motion to counteract lunar gravity. Small attitude control thrusters maintain the vehicle's orientation during the burn. The vehicle needs a highly accurate navigation system to determine its position and velocity. In cross-section, the propellant tanks hold the fuel and oxidizer needed for the main engine burn. The total amount of propellant directly dictates the maximum payload mass that can be delivered. Large composite tanks are engineered to contain cryogenic or hypergolic propellants. The pressure regulation system ensures a steady flow of propellant to the thrusters. Now we look at the guidance system, which must execute the precise landing sequence. The descent is broken into several phases, starting with the braking phase from orbit. The lander uses a combination of radar and inertial measurement units for navigation. Lidar sensors measure the exact distance and velocity relative to the lunar surface. The hazard avoidance system uses cameras and onboard software to identify safe landing zones. This system detects large rocks and steep slopes, autonomously diverting the descent path. In the final meters, the lander enters the terminal phase, slowing to almost zero velocity. The main engine cuts off, and the lander free falls the last few meters to the surface. Shock-absorbing landing legs dissipate the remaining kinetic energy upon touchdown. The lander must orient itself correctly to protect the sensitive science payloads on board. The touchdown is signaled by a contact sensor on one of the landing pads. Upon successful soft landing, the CLPS provider receives the full fixed-price payment. Next, we examine the types of payload CLPS is delivering to advance lunar science. Many payloads focus on characterizing the lunar exosphere and the radiation environment. Cameras and imaging systems map the landing site geology and the surrounding terrain. Small rovers are deployed to explore local areas and demonstrate mobility technology. On the diagram, a rover descends a ramp from the lander's deck, preparing to explore. These early missions also test hardware and systems needed for the Artemis human landings. For example, specialized drills test the ability to penetrate and sample the lunar regolith. Science packages are designed to operate for at least one lunar day, about 14 Earth days. Survival through the 2-week lunar night is a major challenge due to the extreme cold. The lander's solar panels provide power for both the science instruments and the spacecraft systems. Excess power is stored in batteries for periods when the sun is obscured by the moon. The lander is also a communication relay station, sending data back to Earth via its antenna. This constant communication link is vital for mission controllers and for data transmission. Now we compare the CLPS landers against the Apollo lunar module for perspective. The Apollo lunar module was designed for 2 astronauts, carrying a large habitat and ascent stage. By contrast, CLPS landers are smaller, robotic vehicles designed only for cargo delivery. The Apollo mission structure was fully government-funded and operated by NASA. The CLPS approach relies on commercial providers to own and operate the vehicles. Apollo landed at 6 equatorial sites, but CLPS can target a much wider range of landing zones. This flexibility allows access to new science targets, such as the difficult South Pole region. Now we look at 2 major CLPS providers and their specific lander designs. Intuitive Machines developed the Nova-C lander, a medium-sized vehicle with a methane engine. Nova-C is designed to carry approximately 130 kilograms of payload to the surface. Astrobotic technology built the Peregrine lander, which uses a traditional hypergolic propulsion system. Peregrine can carry various small payloads and focuses on a quick turnaround time. Both companies leverage existing commercial space technology to meet NASA's delivery needs. The competitive landscape pushes each company to constantly improve efficiency and reliability. This approach is meant to stimulate a sustainable commercial lunar economy for the future. The initial missions proved that the challenges of lunar logistics are very real and complex. A key challenge is managing the extreme thermal environment from scorching day to freezing night. The landing hazard avoidance system must operate reliably and autonomously without human intervention. Accurate navigation is essential because a slight aiming error can result in a hard impact. These early missions provide invaluable flight heritage and data for future human-rated systems. The lessons learned from the first CLPS flights are directly improving the lander designs. Now we address a common misconception about the reliability of this commercial approach. Some believe that commercial providers are inherently less reliable than government agencies. However, the fixed-price, pay-for-performance model incentivizes success and mission reliability. Companies are highly motivated to succeed because their reputation and future contracts depend on it. The CLPS program includes NASA oversight and reviews throughout the development process. This collaboration ensures that the mission safety and science requirements are strictly met. Therefore, the commercial model provides both cost efficiency and high standards of technical performance. The CLPS landers are the vanguard of NASA's Artemis program to return humans to the Moon. The science payloads are preparing for the arrival of astronauts, for example, by scouting resources. The landers will eventually carry critical infrastructure, such as power stations and habitat components. Zooming in on the lunar South Pole shows a potential landing site for a future CLPS mission. The delivery service is paving the way for a permanent human presence on the Moon. On the diagram, we see a possible future where multiple landers and rovers establish an outpost. The logistics chain is designed to be scalable, supporting a growing number of missions annually. This rapid commercial development is a major driver of the new space exploration era. The CLPS strategy ensures that NASA is not dependent on a single vehicle or single launch provider. This redundancy strengthens the overall lunar logistics network and increases mission flexibility. Ultimately, the CLPS program is building a reliable and affordable delivery service to the Moon. This delivery service is crucial for establishing the lunar base camp required by Artemis. The landers are proving the technologies needed for safe and precise deep space navigation. The commercial providers are rapidly improving the capabilities of their lander vehicles. This partnership is a new model for space exploration, leveraging the speed of private industry. The next few years will see a dramatic increase in the amount of cargo delivered to the Moon. This growth in capability is the payoff of NASA's innovative CLPS program structure. In summary, CLPS uses fixed-price contracts to build a private lunar logistics chain. The landers must perform a complex journey, including a soft landing using precise navigation. These missions are delivering science payloads and preparing the way for human exploration. The competitive model drives innovation and lowers the cost of access to the lunar surface. The success of CLPS is vital for the larger Artemis goal of sustained human presence. The future of lunar delivery is commercial, reliable, and scalable for permanent operations. The Moon is no longer a destination, it is the next logistical node for science and resource development. This new capability ensures a long-term American presence on the Moon and beyond to Mars.